Okay, welcome to the final lecture for this workshop. Today I will present some kind of examples of actually running a software for molecular dynamics, showing some examples, and talking about the method a little bit in more details instead of instead of the physics of the specific process we are interested in. So I'll start with this slide which I had shown you a couple of lectures back when I was talking about MD theoretically as an algorithm. The bits and pieces of this are very important, and today what we will see is how do you actually do it. I mean, how do you execute this process, calculation for a specific kind of example that I will present. So without further ado, let's get started. So when we talk about implementing molecular dynamics, the first question that comes to your mind is what is a good software if you're getting started in this, right? And there are multiple software starting from in-house codes. In fact, the first software or code that I started with when I was a PhD student was a code written by my co-advisor, Professor Murad, and it was written in Fortran 77 back in late 70s. So it was not very efficient. It was not parallelized. Back then, there was no opportunity to kind of run them in parallel on multiple processors. But today, we have quite a few open source as well as commercial codes. The ones that we use for molecular dynamics are mostly open source, fortunately. It's not, what that means is you can not just implement the code for your problem, but if needed, you can get in there and make changes to the subroutines in the code. Some examples are in here. The most popular ones, of course, there are many more besides these. There's LAMMPS developed at Sandia National Lab, which is pretty versatile and is used quite a bit for modeling condensed matter systems, particularly crystalline structures, grain boundaries, and so on and so forth. But it's not limited to that. You can certainly use LAMMPS for many other different situations, looking at membranes, even biochemical systems like proteins. But for that matter, NAMD developed at Urbana-Champaign is much more well suited for looking at macromolecules and polymers and proteins and those sort of structures. There is GROMACS, which comes out of the University of Groningen in Europe, which is very, very efficient. I really like GROMACS. I've used it quite a bit for my work, especially the calculations that I showed you earlier with deposition of particles on interfaces, looking at solvated systems. GROMACS actually does a good job. And I'll speak to why that is the case. I mean, this software essentially runs the velocity-Verlet algorithm in here, right? That's the major piece of the molecular dynamics simulation. This is the algorithm that it has to kind of work on. That's the central piece. But there are other aspects, which is pre-processing and post-processing, which some of these softwares have built-in modules to do that. And that's why I like GROMACS quite a bit. They have many different modules to post-process or pre-process. There is DL Poly, which was developed for polymers out of Daresbury lab in the United Kingdom, and it's not as popular as the others, but for some specific applications such as polymers, it's widely used. And then finally, there is CHARM and AMBER. They are not only known for their software, which is mostly looking at organic matter, but also for the pair potentials. They have their own. The software developers have their own pair potentials. It's like you have the periodic table. It doesn't get into F electron systems and transition rare earths and transition metals, but for the first few rows in the periodic table, they have it pretty much mapped out, those pair potentials. Leonard-Jones-based pair potential, both CHARM and AMBER, and they're also very popular. The key aspect for most of these software are, like I said, they're open source and parallelized. Some of them are massively parallelized. For example, LAMMPS is one of the most efficient software out there for running on massively parallelized systems. You're talking about thousands of cores if necessary. So is NAMD. NAMD is also massively parallelized. So when you look at software that are parallelized, one of the key things that you look at is how is the latency of this, in the sense, if you're running them or launching the job on, let's say, 1,000 cores, what is the time spent in the calculation in communicating between the different nodes? Because the way parallelized molecular dynamics works is through domain decomposition. It kind of breaks down a collection of particles and gives them out to different processors to run the velocity Worley algorithm. So how much time is spent in communication and latency compared to the actual calculations themselves is a good scaling analysis or scalability analysis. Most of these codes are actually run on Linux and Unix terminal. All the work that I do with molecular dynamics is pretty much Linux and Unix. So all my computers pretty much either run solely on Linux or they're dual boot. It's how these calculations are run, in the sense they can take advantage of scripting languages. The Bash and Python scripting is pretty convenient to call and use those routines from a Linux environment. All high performance compute systems are based on Linux environments, so that's how you run these calculations. But some of these software do have versions out for Windows, and that's the one that I recently loaded, LAMMPS, on this computer. I don't use this Microsoft Surface for calculations, MD simulations. It's not equipped to do that, but for very simple systems, perhaps you can do a short calculation, right? So LAMMPS and a few other software do have them in Windows platform as well. Most of these codes are written in either C++ or C, and there are some legacy codes that are in Fortran. I'm talking about, when I say codes, I'm talking about the molecular dynamics software. Okay. Questions about software? Okay. So if we break it down in terms of what we exactly do with this software in terms of executing a calculation, the major steps are pre-processing. It's like sample preparation if you're an experimentalist, right? The first step is, before you characterize your material, is to actually make it and prepare it for the sample to be used for characterization. Same deal with molecular dynamics. Sample preparation essentially means developing an initial configuration that you can then evolve in your molecular dynamics software to a energetically more favorable state, right? So coming up with that initial configuration and an input file for the simulation, and we will look at examples of the input file with LAMMPS today. There are many software that are very well suited to help you generate these input files. The one that I use pretty much most of the time is called VMD, Visual Molecular Dynamics. This too is developed in Klaus Schulten's group at Urbana-Champaign. It's very good for a diverse range of systems, from crystalline systems to protein, whatever you're interested in. VMD has modules that help you kind of develop the simulation box itself. So let's say you're interested in developing a crystalline structure, or you're interested in developing a box with a liquid, water, with fullerene, whatnot. Then these software help you develop that. There is a software, Avogadro, which is widely used in the chemistry community. It's mostly to develop chemical structures, molecules, and energy minimize their structures, relax their structure to the right states in terms of the bonds, angles, dihedrals, right? So it's pretty straightforward. Again, it gives you a periodic table, and you pick elements and construct a molecule. Once you have it, you typically use a force field such as amber or charm, which is very diverse, not super accurate, to kind of relax the structure. There are others like PacMol and Vesta that are also used in this community. I'm just started exploring Vesta. It looks like pretty well equipped to develop crystal structures as well. I don't know, has any of you explored Vesta? You have? Okay. And PacMol is quite well equipped to work with LAMMPS. Okay. A lot of times folks use PacMol. So sometimes MD software have module to pre-process as well, like GROMACS has GenBox. LAMMPS has functions that you can call to generate a crystal structure, a grain boundary. Okay. It's not as straightforward, but it typically involves a set of steps to develop it, but the software itself can help you easily generate a FCC crystal structure or a BCC crystal structure, some simple structures. Okay. At that point, the next step that is super important is identifying the force field, which we have talked about at length. So I'm not going to repeat that, but also preparing, specifying the parameter file, the force field parameter file. Let's say you are using EM potential. You will have there is a great database at NIST, okay, where you can essentially pick all sorts of library of EM potentials. You take that file, you put it in a certain folder within your software so that you can call that file, and that file has all the information. For example, if it's mean potential, then you're talking about embedding functions, the atomic electronic density, the configurational part of that potential. So all those information are typically recorded in that file, and all you're doing is saying, well, in my box, the atoms I have are actually copper. So that's how this is supposed to behave. We'll look at an example. So this is all pre-processing. Questions about pre-processing? The goal of the pre-processing step is to make sure that you're feeding a meaningful information input, including the configuration, force field, and input file to the software, because that's super important, particularly the initial configuration. If, let's say, you are looking at a membrane sort of a structure, and somehow you have molecules or atoms that are pretty close to that, I mean within, let's say, 1 angstrom erroneously, then what happens when you start your calculation? Your MD simulation software detects a very high energy. If you think of pair potential, there is a kind of a high repulsive function at small distances, and that will try to correct by, from that energy you get a high force, and therefore, it speeds up that atom, and there are problems that you face. The system blows out a lot of times because your Verlet algorithm is unable to use the time step you have specified to kind of integrate the equations of motion. Questions about pre-processing?
Can we identify any mistake if we have committed in that pre-processing step itself before going to the next step?
Yes, you can. Usually there are steps. For example, whatever visualization software you're using, like VMD, what it does, it loads up your simulation domain, and you can, it has some functions. You can identify if 2 atoms are too close than what it should be. Sometimes these software have a small energy minimization module that you can run to remove those bad contacts. And then, so that's about the configuration. As far as the force field goes, no, I mean, you're on your own. You have to just make the right judgment, pick the right force field, and make sure that, you have the right parameters. There's no such tool that kind of can tell you what to do. Same with the input file. But the configuration that you're developing, which is the main part of pre-processing, you can visualize the configuration. If you clearly see there is overlap, there's a membrane and polymers are kind of going through it, which it shouldn't, then you have to correct it somehow. Equilibration is the next step. I mentioned this a couple of lectures back. Equilibration is like starting from this initial configuration and moving towards a configuration that is meaningful. And in today's example, I'll show you how a system can be equilibrated with lamps. So how do you do that? There is no one recipe for equilibration. Again, you are starting, I'm sorry, why is that doing that? You're starting from a high energy state. So this is, let's say, configurational potential energy, and this is time. And you want to evolve your system to the minimum energy state, right? Now, this can be, how this is done is not so important as long as you're doing it efficiently, meaning using the least amount of compute resources, and you have achieved that minimal energy configuration, you're good. Now, there are some tricks in the community, some standardized processes to do that. For example, you start with time steps that are smaller a lot of times. If you have tricky systems that you're not sure about their configuration, you start with small time steps, because what that does is in your Verlet algorithm, essentially. And if I can perhaps go back here, I have the Verlet algorithm. Yeah. So, if you start with small delta t, the system can self-correct sometimes, in the sense, even if it has a very high acceleration because of a high force, due to some sort of a error in the configuration, it can integrate the system to move towards a favorable state. So it's sensitive to this delta t, the time step for integration. So that's one trick that you can oftentimes use for a rather tricky system to evolve it during equilibration. The other is you can equilibrate in steps. You can first do a static energy minimization, which means it's essentially a 0 Kelvin energy minimization, but it's not DFT. You're still doing that based on the force field that you have specified, but you're doing it without capturing any dynamics. There's no time step. And then you follow that with, so you have a crystal structure. I'll show you an example later for aluminum crystal. And you start off with a lattice parameter that is off. Okay? It's smaller than what it should be or bigger than what it should be. So you want to relax the system to the right lattice parameter to get the right properties. And so, a static minimization can do that sometimes. But then there is also dynamic, like a proper MD simulation that you can run for several picoseconds, hundreds of picoseconds, nanoseconds, depends on your system. Let's say you're relaxing a protein structure in a solvated environment. These equilibration runs can sometimes take 100 nanoseconds or more. So yeah, depends on how long you will run for equilibration. You have to basically monitor how the energy is behaving. If it's going down like this, you keep running, and once it's kind of flattened out, then you say, well, my system is equilibrated. Okay. Yeah, I think I mentioned this. There are two types of static energy minimization that LAMMPS, for example, employs. One is called the steepest descent. The other is called the conjugate gradient. That's just the algorithms. Finally, let's say you have a system which is physically meaningful. You have a aluminum crystal structure that makes sense, agrees with experiments, and you want to kind of simulate some sort of a mechanical behavior with it or calculate some property. At that point, what we do is this process, the production run, which is basically the trajectory that you generate. Yeah, go ahead.
Suppose we want a system not at an equilibrium position, means for the metastable phases, or sometimes we get some lattice parameters which are not actually at the minimum energy. So I don't want to do the energy minimization. So means if I will be going to the relaxed structure, so I will be definitely leading to a lattice where all the parameters will be the equilibrated one. So I want to have the lattice parameters which are actually I am getting in the my experimental conditions.
Oh,
so
okay.
Then can we do these type of calculations, and is it fruitful or is it meaningful?
Good question. So just to repeat that for everybody's benefit, the question is, what if your measured lattice parameter from experiment is different from what you get by minimizing the structure? That typically would mean your force field is not suited for that problem. So you have to look elsewhere for a force field that is able to capture your measured lattice parameter or structure that you are interested in, that particular phase, crystalline phase.
No, I want to mean
Yeah.
that I have a crystal structure.
Mm-hmm.
I mean, with a particular lattice parameter. I want to know the properties of that particular lattice structure. So with specific lattice parameters.
Mm-hmm.
So without doing the minimization, because if I am going to do the minimization, so structure will be relaxed and it will try to get the equilibrated lattice parameters.
Right, but even if you don't do the static energy minimization, even if you just ran an MD simulation, it will try to converge it to the same. Yes. Now, if you are interested in that process of how that relaxation happens, for some reason this is some phase transition that you're interested in, you start with a structure which is not captured from the energy minimized structure in your force field, but you want to study how it goes from that initial structure which you specify to the final structure based on the force field. If this is a process you're interested in, you can run a calculation so that will be a non-equilibrium calculation. For example, even for the deposition of PCBM, that's that process. You're starting with essentially a higher energy state where the PCBMs are not deposited, and it's exploring the phase space to ultimately find a location on the surface and deposit so that it reaches the energetically meaningful structure. So routinely we do non-equilibrium simulations. Does that answer your question? But for specifically crystalline system, if you have a force field, it will capture a certain structure from that. Okay. Another example of a non-equilibrium calculation is, let's say you want to calculate the thermal conductivity of a crystal, right? You can impose a temperature gradient and look at the response to that temperature gradient and from which there is either a Green-Kubo or Muller-Platte formulation to kind of estimate the thermal conductivity of that material from that. Obviously, it's non-equilibrium because there is a gradient, in this case a temperature gradient. Yeah. Okay. So, where was I? So, I was talking about the production run. Essentially what you get out of production run is the raw data is the thermodynamic properties of the system as it evolves from one configuration to the other, and some of those parameters that you can print out are temperature, configurational energy, pressure, volume, density, virial, kinetic energy, bond energy, and so on, as well as just the configuration itself, which is the evolving structure of your system, basically the atomic coordinates as the system moves from one state to the other. And then if it's an equilibrium calculation, you can use this to calculate ensemble average, which I am saying loosely because it's really not, it's a time average, but you understand what I am trying to say here.
Can you calculate heat capacity of solid substance like steel and?
Yes, you can calculate heat capacities as well, though heat capacities are more accurately calculated using, unless you have a super accurate force field for a certain system. Density functional theory is used more often to calculate heat capacities with MD rather than MD. So, that's the raw data that is generated. So, now much like experiments, you have characterized your system and you have generated some raw data, and you have to analyze it to get something meaningful, to understand some physical behavior of the system, whatever you're interested in. And there are many things you can do. You can post-process the raw data to simply look at the structure. Using, in MD simulations, the most straightforward description of the structure is through pair distribution functions between two different atomic species or two different molecules, their center of mass, whatever you're interested in. You can gather lattice parameters and also functional properties of the system, such as, when I say functional properties, it's some mechanical property, bulk modulus, maybe thermal conductivity, whatever you're interested in. Examples of those are, like I mentioned, also self-diffusion coefficient, stiffness, and viscosity. You can also measure energy barriers. A lot of times the post-processing can involve a separate calculation itself, like umbrella sampling. I'm not going to get into details of that here in this lecture, but any questions about post-processing? Okay.
So, sir, in thermal conductivity, we usually have contribution from the electrons and the lattice.
Mm-hmm.
It's vibrational thermal conductivity. So, is it vibrational one or everyone is?
This one that the MD simulations captures the phononic vibrations. It is not able to get into the electronic contribution in a straightforward manner. But it's indirectly speaking, if you, for example, apply a temperature gradient and look at the temperature distribution in response to that as the system equilibrates, and if the force field is accurate, the calculated thermal conductivities do agree pretty well with measured thermal conductivity. But no, it doesn't separate it out in terms of electronic contribution and phononic contributions, right, which DFT simulations would be able to do. So, what are some of the common things to watch out for while you kind of run these calculations? Obviously, one of the most important one is making sure your system is equilibrated. And like I mentioned, the best way of checking that is routinely outputting the characteristics of the system. The thermal properties could be configurational energy, the temperature, pressure, and making sure that its system is behaving in a way that you expect for an equilibrium, for equilibrated system. If it's still converging, so if the energy is still converging, then it's still dropping, let's say, the configurational energy. That means it's probably needs to be extended a little bit more till you get constant value. The second one that is very important, obviously, is the input, the force field. Without I'm not going to talk about it. We have discussed this. Third one is cutoff distance that you specify to your either Coulombic interaction potential or the Lennard-Jones or whatever interaction potential you're using. If you don't have a cutoff, your simulation will be very slow because at every step you're looking at NC2 pairs. n combinatorial 2, and that's a huge number for a system of, let's say, 100,000 atoms. So you don't want to do that if it's not necessary. So you basically have to specify a cutoff to your potential beyond which you say that it doesn't change, and therefore I only account for interactions within 15 angstroms or 13 angstroms. So if this cutoff, on the other hand, is super low, let's say it's less than 10 angstrom, which is what it used to be back in the 1990s a lot of times, simply due to lack of compute power or compute resources, then you are incurring some error due to a small cutoff. It's not a huge problem these days. The time step has to be carefully equilibrated. There are two considerations. One is obviously the compute efficiency. If you use a time step that's needlessly small, then your simulation will run longer, obviously. On the other hand, if you're using a time step that is too large, the system might not be able to converge. So there is a lot of times you have to run a sensitivity analysis to make sure you're using the right time step. It can also be related to the physical or chemical process you're investigating. A chemical reaction, for example, you might need to look at resolution at much smaller time steps, typically 0.1 femtoseconds, to capture a certain chemical reaction you're interested in. Another aspect is how big of a system do you want to simulate. Obviously, we want to simulate the smallest system that we can to get an accurate estimate of a parameter property that we are calculating. But a lot of times, if the system is too small, it simply doesn't capture, right? You're either not doing enough sampling, or there are some periodic interactions that become spurious. Especially, I would mention this if you're interested in modeling a macromolecule like this, and if you're using a periodic boundary condition, remember you are capturing its replicas, right, in all 3 dimensions. And a lot of times there can be spurious interaction between one end of that molecule with its tail end across the periodic boundary, which you have to be careful if you want to avoid that. You have to have a certain size of the box to eliminate those interactions.
Sir?
Yeah.
Sir, in this case, sir, you talked about the cutoff distance for the potential. But sir, in general in DFT, we don't account for the potentials. We use interaction-free systems. So, sir, in that case also, but we need to see the cutoff for the steps to be.
That's the cutoff energy you're talking about, probably.
Oh, that is the energy.
Energy cutoff in DFT. We are talking about the cutoff distance for the pair potential. So
here, sir, the distance we have to
right.
cut off.
Yes, you have to say that if 2 atoms are beyond a certain distance, okay, then we will not consider interaction between them because you can analytically calculate that interaction, and it pretty much contributes very little, nothing probably. So it doesn't make sense at each step to calculate all pairwise interactions in a large system. So you're needlessly using compute resources there. And like I'd mentioned the other day, the computational time is proportional to n log n, where n is the number of atoms, so it's nonlinear. So you double your system size. By system size, I'm meaning basically those interactions. You just don't double your compute time. You're increasing it more than double. So you have to be careful. Yeah.
I presume there's boundary conditions besides periodic boundary conditions that you
Sure.
can impose, right?
Yes. So for example, the software LAMS, it has many other boundary conditions besides periodic. Number one, it can be periodic in certain directions and not in all directions. You can have shrink-wrapped boundary condition where you're letting the atoms on that boundary kind of go beyond, but you're still keeping it within the domain. There are a few other boundary conditions. You can have a fixed wall. Yeah. But then you have to think about physically what that wall implies in terms of the mechanical stress that it introduces to the system. So yeah, periodic boundary conditions though are very popular.
There are more than 2 atoms interacting. Like there are three body interactions.
Yeah.
And you are considering the 2 atoms interacting. If there are 3 interactions and 3 atoms interacting together.
Not necessarily. There are potentials that are many-body or multi-body potentials. For example, Tershoff potential, Finis-Sinclair to a certain extent. So not all potentials are just 1-to-1. There can be an angular term. For example, even in mean potential, there is a term. Yeah. Leonard Jones is pairwise, but not everything is pairwise. Right. It doesn't take into account like triad interaction, right? I mean the angular aspect from that. But there are potentials that do that. There are multi-body potentials, not necessarily all are pairwise. Okay. So at this point, let me introduce you to one example of a software, like I said, that is very popular in this community. It's called LAMS. Some of you are nodding your heads. You're probably already using this software and are familiar with it. So the reason LAMS is popular is it can address very many types of materials and configurations that we need to look at. It's very well documented. So the LAMS manual is updated frequently. They also keep fixing the bugs. Not all software do that. So every couple of months, LAMS comes out with a new version where they fix bugs. All software have some sort of bugs here and right, but LAMS does a good job in periodically addressing those. And then, besides the manual, if you simply Google LAMS and any keyword that you use in an input file, it brings up kind of the description of that and how you got to use it, as I'll show you. So if you go to LAMS site, you see a lot of example scripts. I haven't linked it here, but basically, probably at this point, I can start sharing my screen. Can I share my screen? Oh, I don't have internet. It would be nice to have internet here. Usually
because people are online.
Yeah, but I'm not connected.
No, you are not, I mean, maybe the main computer is connected, but not your iPad.
Yeah, this is not connected. Yeah, this is. Is there a way I can get connected to internet? It needs a user.
You can use Wi-Fi, sir.
Mm-hmm.
You can use Wi-Fi.
But all the Wi-Fi are password protected.
Yes, sir.
So they are secure Wi-Fi. Is there a way I can get someone to? Thank you. The guest? He's helping me get connected. Thank you. It's probably all right. If it doesn't, then I think I have most of the files. I won't be able to show the site itself. But you can, of course, visit LAMS, just Google it, and if you haven't already done that. And you see a lot of cool videos and example files. So if you're getting started with MD simulation, that is very helpful. This is not sharing my screen now. It's not connected. That's fine. I can manage without that. But okay. So what I did was I was looking. Like I said, most of these software are based on work on a terminal, a Linux terminal. But when I looked at it, LAMS has a GUI now. I think this is kind of recent. This GUI that you can use to run on Windows. So it's pretty useful. Have you guys explored LAMS on Windows, the GUI? I hadn't in the past. I mean, I think this is kind of recent. And I played around with some of the example simulations that are in the LAMS directory, and proved to be pretty straightforward. So in the past, to run a LAMMPS calculation, you have to use the terminal to have your folder with the input file, link it to the the force field file, and it will run through the terminal. But now this one is based out of Windows, so in that sense, it's useful to get started. So if you download LAMMPS, it comes with the source files and everything and the documentation, and this is the folder that I was referring to. Examples. I can increase the font size here. Maybe it's difficult to see it. Yeah. So each of these folders correspond to some sort of a computational experiment, if you want to call it that, for very many different kinds of systems, materials, and different potentials. For example, there is colloidal systems, there is crack propagation, there is, I think there is one with grain boundary, there is a simple tensile kind of a calculation that you can run to look at tension, the effect of tension, and calculate properties. Of these, I picked a couple to kind of show you and run for you here. Small systems that can be run in a few minutes as a showcase or as an example of how you might be able to use this software. So the first one that I will use, and this was developed by Mark Schopp, I believe, who is at ARL, and Andrew Ferguson at University of Chicago, as kind of again a short tutorial of how you can use. These are simple input files. So if you open up LAMMPS, the first step is basically to open the input file you are interested for the system you're trying to model. So go to my folder and open, in this case, this particular input file. So this is an example of an input file. Like I mentioned, what an input file does is it basically describes the system. A lot of times it helps develop the initial configuration, which this crystalline structure for this one, it's pretty straightforward. So the structure is developed in the input file itself, and it then has the setup of the thermodynamics, all the variables that you want to output from your calculation, and the trajectory. So the input file is what it directly communicates with the software to model the system, right? And the only separated file that is used typically is the force field file. In this case, the name of this is for aluminum, an FCC aluminum lattice structure. So the force file was downloaded from NIST. I'm trying to zoom in a little bit more so that you can see it. Let's see, Control plus. For some reason, it doesn't zoom in beyond this level. Can you read this file, or is it too small, the text? It is readable to a certain extent. Okay, so let's go with this. So there are various sections that an input file is kind of set up in. The first section, the most important one, is what units are you going to use for your calculation, right? There are many unit systems in LAMMPS. My internet is not connected, but if you want to Google, LAMMPS and units, just LAMMPS and units, you will see some of the common units are Lennard-Jones, real units, metal units. The way these are different is all the properties and dimensions that you're trying to model. For example, distance in metal is in angstroms. In some other unit system, it could be in nanometers or picometers. So in Lennard-Jones set of units, everything is non-dimensionalized. So length units is basically the real length over a sigma parameter. So the units are very important to look at when you specify in the input file. Then it kind of sets up the system in terms of the dimensionality. In this case, we are trying to develop a simple aluminum crystal and trying to minimize it to get the right lattice parameter and cohesive energy that can come out of it. So you set up a dimensionality of 3 and the boundary condition. So in this case, it's a bulk crystal that we are trying to model. So it's PPP, meaning periodic, periodic, periodic in all x, y, z direction. Okay. The atom style here is atomic, so it tells the system that we are looking at a set of atoms. If it's a molecule, then it will be treated in a different way, or so in this case we are looking at a simple aluminum, so it's atomic. The next one is how do you create the atoms and the region in space that you want to develop your crystal in. So, in this case it's aluminum FCC crystal. So, this command lattice sets it up as FCC with a lattice parameter that needs to be supplied, and we have kind of randomly supplied a lattice parameter of 4 angstrom, knowing that, yeah.
So that means if I am trying, I mean, I don't work on this thing.
Sure, sure.
But if I am going to develop lattice for iron, for example,
sure.
So I will write lattice
BCC.
2, something like that.
Right.
With the number of atoms in every cell, right?
Yeah.
Okay.
You have to specify the lattice structure depending on how complex your lattice structure is. You know, for FCC, BCC, it's just that one parameter. For other types, you will have more parameters that you have to specify. It's pretty straightforward in labs. The lattice constants.
So 4 was the lattice constant.
Right.
So it's not number of atoms in the system.
No, it's not the number of atoms in the system. It's the lattice constant, 4 angstrom.
4 angstrom.
It is 4 angstrom. The number of atoms, and you will see how we set up the number of atoms in a moment. So you basically set up a region, a box, which is basically a block structure, and you know you have a lattice units in there, and you can basically replicate the box later. In this case, we replicate it to 2 by 2 by 2. So there are 2 times 2 times 2 lattices, 8 lattice structures in there, unit cells basically. You can orient your crystal in various you can develop crystal with different facets in the x, y, z direction. In this case, it's 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? And then you populate your box with atoms. So now you have a region in space with a physical lattice structure, and you fill it out with the specific type of atom you're trying to model. The software still doesn't know what atom you're filling it up with, because we haven't specified the pair potential. And then you replicate this box however many times you want to do. We are modeling a small system because these are kind of expensive calculations if you look at much bigger systems. So the next step is very important. You have to specify the interaction potential. In this case, it's the embedded atom model and the file that is associated with it. And this in general can be many different parameters for various types of atoms in your system. In this particular case, there is only aluminum, so there is only one type of interaction between aluminum and aluminum. But if this were an alloy, you will have, you know, aluminum with the other element. If it's a high entropy alloy, there will be many such elements, and you have to basically specify all the interactions that are happening between the different atoms in the system. Now, you might be thinking, well, these interactions are between aluminum, aluminum. What about the cross interactions? There are mixing rules. For example, you know, one of the popular mixing rule is called Lorentz-Berthelot mixing rule. So, mixing rules can develop arithmetic averages or geometric averages of parameters such as sigma, epsilon parameters in Lennard-Jones to calculate those cross interactions. It depends on your system. In this case, we don't need those interactions between different types of atoms. The next step, yeah.
Is the code smart enough that if you told it to do BCC aluminum, that as you calculated it, it would switch to FCC?
It depends on the code will rely on the force field that specifies the interaction. So let's say incorrectly you used a different force field for iron, and on the other hand the mass and everything else you have is set up as aluminum. It will result in it will result in the structure of the BCC structure, because the force field you have specified is for iron. So it's all reliant on the force field that captures those interactions and relaxes it. This one, to answer your question, for this aluminum EM potential, even if you started with a completely incorrect kind of lattice parameter or even a crystal structure, eventually it should relax itself to the right structure based on the potential. Right. So yes, it will eventually do that if you have specified the right potential parameters. There are many numerical aspects. There are some physics aspects like the interaction potential. By the way, the interaction potential, if you're thinking, how does the file physically look? I mean, where is the file even located? So in this case, there is a folder with various potential files included in it. Let's see where it is. So these are the potentials, and you see a bunch of files, right? These are all files for different parameters, and you see the names of these files. For example, there is gold, aluminum oxide, aluminum copper. So, and not just that, there are organic species. For example, carbon hydrogen arable, which is a bond order potential. So this folder is populated with standard potentials that are very frequently used. Obviously, if you are modeling a very specific system, like you mentioned, a high entropy alloy, and that potential is not already kind of supplied in LAMS, then you will have to find those interaction parameters from a database, right? Let's say NIST has a pretty good database. Copy and paste it to this folder and employ. As simple as that. But there can also be the situation, on the other hand, that you're looking at a composition which has never been modeled, or you're introducing an element in your high entropy alloy which doesn't go with EAM. Then what do? That's a challenging problem. Then you have to first run calculations to parameterize the force field itself, right? That could involve a bunch of DFT simulations or machine learning based calculations to connect the structure to the properties of it and therefore parameterize the potential. That's a problem in itself. Very frequently we run into that problem where the potential parameters are not available. For example, the amorphous glass structure that we modeled, sodium sulfide, sodium silicon sulfide, the parameters were not available for sodium. What was available was for lithium silicon sulfide. So we had to parameterize, we have to come up with our own parameters for sodium and specify it. But what you can take advantage of is it doesn't have to be an entirely new format. Let's say you are introducing a new metal to a high entropy alloy for which the parameters are not specified, but you still can use an EAM or MEAM type potential model. So all you have to do is go into a standard format for that file. Let me open one up, the one that I'm using as an example. Where is it?
Can you open these files or what?
This one is the one I'm using. What's that?
Can you open this file? What is the inside?
Yeah, that's what I'm doing. Yeah. So this is there is a format. There are manuals for these. So what these parameters are, you start out with these parameters, right? So these are probably the parameters for the embedding function, the atomic electron density, and the configurational interaction. You have to kind of look up the functional form of that particular potential, in case the EM potential, and then supply those parameters for your specific new element in the periodic table that you're trying to model. That's about it. Okay, so from the input file, you're basically calling the pair potential. So these are some of the physical aspects. Now there are some numerical aspects involved here, or computational aspects. For example, these two lines here, neighbor 2.0 bin. What is this supposed to do? So it's not very efficient as a software for LAMS, let's say, to continuously have to track what are the set of atoms that are within a cutoff distance that it has to account for. So you can maintain a neighbor list for each atom, right? It's like a library. For each atom, you know what its neighbors are supposed to be. You don't bother updating it. You just update it every, let's say, 10 steps of the calculation or 20 steps of the calculation, except if you detect that one of the atoms there has moved more than it should. Let's say in this case you specify 2 angstrom. So if it has moved 2 angstrom, probably it's somehow rearranging itself or something is going on, so I have to update the neighbor list. So these are the computational aspects. Okay. And then LAMS has the flexibility of defining variables and computing them every step. So you can.
So what is this delay time?
Oh, delay. So that is how often do you want to update your neighbor list? In this case, you're saying
like
every 10, every 10 time steps. Okay.
And what is that 2 signifies there?
The 2 is how big should be, or it's called the skin thickness. Basically, how much do you want an atom to move to trigger that, well, we need to look at the neighbor list and update it. Yeah. These are, again, it's unfortunate I can't bring up LAMS, but I could have shown, if you can just do LAMS neighbor, if you just search that, you will see a very good description of this. The manual is really good. Just do LAMS and neighbor. It will bring up all the details of how this works. Okay. Okay. The next step, because we are trying to model this system and calculate its cohesive energy, what we need to what we are interested is in the potential energy per atom in this crystal system. So we specify a compute, we call it ENG, and say for all atoms we want to continuously, each step, keep a track of the potential energy per atom. It's a variable we are interested in. And then we are performing a compute function. What this is doing is from it, it's calculating the total potential energy of the system itself. Okay. Next, what are we interested in? We are interested in the trajectory. We want to get the raw data for as the simulation evolves with, right? So this command dump, what it does, it outputs. It's an output command, what you want to output. In this case, what we are saying, we want to output all atom coordinates in this system at an atomistic resolution, and every time step or every step, so the how frequently you want to do that, and we want to record it in a file that we call dump.relax. Okay? You can name your own file. The next part is the main engine of this calculation, what exactly you are trying to do. So far we have set this up. We have created a box, we have set up parameters, we have asked our lamps to calculate a certain variable. But what are we really trying to do? We haven't said that we are going to run an MD simulation. Actually, this particular calculation is not going to run an MD simulation. It's a static energy minimization. So therefore, it says run minimization. The next example I'll show you will have equilibration and production run. So what you're doing is resetting the timestamps. So say start from beginning and relax this box. You introduce a fix to relax this box in an isotropic pressure sort of a setup. You don't want any specific pressure to be applied on the different sides of the box. You want to run a simulation to relax the volume of the box to reach the right lattice parameter that this potential model will drive the system to. Okay? And in the process, every 10 seconds, you want to record parameters such as potential energy, the dimensions of the box, Lx, Ly, Lz, the overall pressure, and the components of the stress in the normal stress, Pxx, Py, Pzz, and the total configurational energy per atom. And these are the thermoparameters, essentially, that your code will spit out as it tries to reach the minimum energy configuration. You are interested in these. The next step is actually the command line which initiates the simulation. It's called minimization style, min style, and you call it CG. Like I said, there are two algorithms, conjugate gradient and steepest descent. In this case, we are running it with conjugate gradient. And there are some minimization parameters that you want to introduce, which is, for example, the tolerance. What should be the tolerance? Basically, the convergence criteria. What should be the tolerance for your force, the energy? How many iterations do you want this to go? You can set this number of iterations to a really large number, let's say 1 million, but there is a chance this code might not converge and keep running. Maybe you're not interested in that. Maybe you're interested in first running it for fewer iterations and then check if it has converged or not. So those are things you can do through these through these variables. Now that you have set this up and ready to start this, the final aspect is what are the quantities or parameters or properties that you want this code to determine from this minimization algorithm, right? We want to calculate the lattice parameters. So you set a variable A to which you're recording the measured lattice parameters. That's something we're really interested in. We're starting with 4 angstrom, but we want to see what it adjusts to. Does it agree with known lattice parameter for aluminum, right? And then we want to record the cohesive energy. So you start a variable E cohesive, ECOH, and define it so that at the end you can print out the total energy, the number of atoms, the lattice constant, cohesive energy. If you're interested in something else, you can easily make it print those things out. That's not a problem. So now we have an input file. Let's try to run it. So this GUI makes it easy. You go to, let's say, this, run the system. It develops this potential energy with time step. For some reason, I was trying to check this. It only looks at the last couple of time steps. It looks like it runs it for 16 time steps to converge. It doesn't really, so there are 2 dots here. It's not very useful. I don't know if this is a bug for the softwares, but the better way of accessing it is this log file it creates. So let's look at the log file from this simulation first, and then we will visualize the trajectory using a visualization software. So the log file, tells you what sort of compute nodes are available for this. So for this particular computer, it's 12 threads that it's running on. Obviously, if you're running this on a high performance compute node, you can run it on, let's say, 100 nodes, each with 16 processors or 32 processors. So those sort of compute details will be provided here. And then it tells you the number of unit cells it's created, 4 by 4 by 4, right? And then it replicates it to 2 by 2 by 2, okay, and creates 32 atoms in this case, right? These are the compute details. For example, the maximum number of neighbors. Usually, if you are interested in making the code more efficient, these are parameters that we'll be interested in checking out, okay? And then you asked it to determine these physical thermal properties, the potential energy, the dimensions of the box, the pressure, these normal stresses, etc., and the cohesive energy, and it provides those to you. What you find is it has only written it for every 10 steps like you've asked it to, and the last step it has written it out at is 16. That probably means that the system converged after 16 energy minimization steps, right? And you can see that the box expanded a little bit in all XYZ dimensions. It started with 8 angstroms and it ended at about 8.10093 angstroms, okay? So we'll visualize it in a moment. It also provides you a bit of a metric about the compute efficiency. So how much time went where in running this code, right? So what percentage of the compute time was spent in determining the pair potential, pair energies? So that's about 11%. What percent of the time was spent in outputting the data? It's quite a bit. You're probably outputting a lot of information, so it's spending 10% of the time outputting. Curiously, I'm seeing that this is the other is spending 78%. This is somewhat interesting because typically, about 80% of the time is spent on pair potential calculation. And if you're running it on many nodes, then quite a bit of time, compute time, goes to communication between the nodes. I haven't really seen in actual calculations and clusters this much time that is spent on other. I'm curious, I'll find out what this other calculation time overhead is. This is atypical. So then it determines here what the various parameters are that you asked it to calculate. The lattice constant, which is expanded to 4.05 angstrom. I looked up the literature before this lecture. Actually, the parameter is 4.05 angstrom. So it does what it should do. You started with an incorrect parameter and it relaxed the structure to the right lattice constant. And it also calculates the cohesive energy per atom, which is negative 3.36 electron volt per atom, because you're using metallic units. If you're using real units, probably this will be in kilojoules or kilocalories per mole. So that's why the unit system is important. And this is also validated because we are just looking at an example. So it gives you the right answer. Okay. Now, if you are interested in visualizing the crystal that you have developed, I usually use VMD. Like I said, I couldn't find VMD, the working version for Windows, so I downloaded Ovito, which is actually getting pretty popular these days. So let me try this out. Let me try to load the structure and see what's going on in Ovito. So this shows you 4 different perspective views from 4 different directions, and this is the perspective view that you can rotate around for this 3D periodic aluminum system. And you can even play a movie. Not much going on here. If you play it really slow, you will see the lattice structure expanding a little bit. The jump you see at the end, it shrinks. Basically, it's playing in a loop, so it's going back to its initial parameter, which is 4 angstrom, and it's kind of expanded out to 4.05. In this example, there is not much to visualize. The next example that I'll show you will have a dislocation that we can look at. It'll be more interesting. So this looks all good. Now what could you change here in this system, let's say, to make it even more accurate? You can certainly go for a much larger system. This is really tiny, 32 atoms. We hardly ever look at 32 atom system. There will be some errors introduced simply because of such a small system. So you could scale this up to replicate the box to, let's say, 20 by 20 by 20. So by a factor of 1000, then you will have 32,000 atoms, right? You could try a different force field. You could call a different potential for aluminum and see what lattice parameter you get from that. If it's more accurate, less accurate, that's a computational experiment you can run. Or you can deliberately start, instead of 4, maybe 3.9 angstrom, and see if it still relaxes to 4.05, which is what you know should be the case. So let's do that. Let's go to run and run this again. And let's see what the output looks like. So now it takes a lot more steps to converge because you started with a more incorrect guess, so to speak, 63 steps, but it still converges to a lattice parameter that is about the same, 4.05. So because your potential model in this case is known to be accurate. So this is a check you will have to run, particularly in situations where you're trying out a new potential that it hasn't been tested. You have to validate it with respect to some of these kind of parameters. So I think before we do the next example, maybe let's take a couple of minutes break, 5-minute break, and then we'll be back to look at another example. Yes. Right. So maybe not with a static energy. I haven't tried static energy minimization, which is a little bit more difficult to converge. Maybe you have to actually run a dynamic equilibration, maybe at a finite temperature, to kind of make it go from that structure to the FCC structure.
I was just surprised to see that I've seen atomistic calculations saying if you do this structure, you're going to get this.
Right.
If you do these atoms, you're going to get this lattice structure.
Oh, what you're saying is, what if you start with a kind of molten structure? It should converge. That's interesting, but I'm pretty confident you'll get it. The reason, in this case, you know the answer. So you take the easy route of kind of, and the other problem, because this is meant for a tutorial, that's how this file was developed, is it'll be a much longer calculation, probably take an hour on this. So you're kind of showing something straightforward. Why it's called aluminum 99? I don't have internet. I have a link to NIST for that. Typically, there'll be a description. I can look it up on my phone, maybe. Why it's called that, aluminum 99. That's a good question. Maybe it was developed in the year 1999. Who knows? Let me look it up. Let's see why that file is called that name. Yeah, it's interesting. The paper is referenced here. Oh, that's true. It was published in the year 1999. I'm thinking it's not a coincidence. Yeah, it's a physical review B paper in 1999. Probably that's why they named it that. So that makes me think there might be a more updated potential for aluminum. Yeah, I mean, that's what you would do at the beginning of a project, explore. For this particular case, it works for the structure, but maybe there's some other property that it's not tuned to. I haven't read the paper itself.
You showed the input file for potentials and 12 or 16
Right.
figures.
Mm-hmm. And then, yeah, it has the electron.
Comment that the potentials come in these.
No. Leonard-Jones, so there are two types of potentials. The Leonard-Jones potential only has two parameters, right? The sigma epsilon. So this one is a multi-body potential, the EAM, so therefore it has a lot more parameters. The more complex the interaction is, the function that you're trying to fit will have more of those fitted parameters, right?
Yeah. I know Mike Bastis pretty well. I've seen him do some of this stuff.
So for example, we were trying to fit a reactive force field for a system a couple years back. That was fitting 32 parameter space.
why the potential cannot be written in terms of equation?
In terms of?
In terms of equation.
It can be written. I showed you the equation. Let me bring it up here, the EAM equation. Oh, okay. Why do you not have, because, yeah, I mean, for Leonard-Jones, you don't have an input file. It's just the expression is known and you're just specifying those two parameters. It's a lot more complex for EAM because it's got a summation of a summation, that function. So you basically develop the library this way that you have those parameters. There are many parameters involved in there. If you look at this file, let me open it up. So you see this one here? It's like a tabulated function here. So potentials can be modeled by just kind of like think of an Excel spreadsheet. If distance versus interactions, sort of numbers that are available, or you can have a fitted equation, nice looking equation like Leonard-Jones, or a power law like Buckingham potential. Morse potential is exponential, e raised to some parameter. So if that's the case, then you just say, okay, these are the two parameters, the prefactors or coefficient. The function is known. But something much more complicated, particularly many-body potential, pretty much all many-body potentials, Tershaw-Brenner, Stillinger-Weber for silicon are like this because they have many parameters that are, it's easier to do it this way than a functional form with a couple of numbers. This particular, no, it's not a function of position. If you look at it, these are just single parameters. These are the electron densities of atoms. Yeah, these are not potential positions.
Potentials, actually, some kind of list of potentials on the file. So should we give us a nice tour again? We saw this new CRF building, we saw the manufacturing. All these names we see everywhere.
Center of excellence and robots. But it's just too hot, too static. But it's
They
good.
have this robotic
TIG meat.
processing and all that.
TIG meat, everything is there.
The six-axis robot. This what?
They don't do it.
Not yet. Nothing. It looks like a lot of it's pretty new and hasn't really done anything yet.
And some
They
more
have a
is
lot of
coming.
fresh, shiny, big equipment.
Yeah.
It's industrial scale equipment.
Right, right.
You know, there is like jig boring machine I have in my lab. There is ocean and laboratory probably. There are two of them, which is not as good as mine here, but they do the precision processing on it. And I have been doing their precision processing. The one Gaurav and she was showing me. So we had some problem with titanium. We were giving some idea of what should be the parameter now.
Driven holes and stuff. Yeah, I couldn't tell that they had done any friction stirring yet, right? But
No.
the equipment's there, and then they have the new
Maybe
big additive system that's additive subtractive both. You know, it's a
They
huge
have
box.
the powder bed fusion, metal additive fusion.
It's not powder bed, it's the powder feed. So you're feeding the powder so you can do gradients as you
I
go.
didn't know that they have that additive manufacturing.
That's the lens. It's the lens system.
even the round easy to see how much you have to pay or even live in a row.
Yeah.
So I see, you saw that high cycle cutting machine. So I have that high cycle cutting machine, and then from the mechanical department they were all telling, you want to do it. I said, okay, you just grab the name and do it. And then I called and said, Professor Bergman, I want to use it. So I said, no, you cannot use it. It's slower. I said, okay. Next time they said, no, you cannot use it. But it's foolish, means it's foolish. And when I insisted that I have to use it, they asked me a charge, which is beyond the top. Yeah, yes. Like
They don't want that.
they were asking like 5,000 or 6,000 rupees for an hour of charge. I need 8 hours to do on the board. I can give to any I can send to Bach, I can send to
The new special price, $200.
Yeah. But now it is, you saw that it's there in the CR, it's there, and the price is okay. And I liked.
Yeah, that's all brand new too, it looks like. I mean, we're asking a lot of questions, they say, well, we haven't tried any of this yet. Just give us some experience. But they said it's not for university too, they said it's for companies.
And the one you went to the nanotechnology meeting, right?
Yeah.
Sati. So that is little expensive. That is.
TN.
Yeah.
And that is a high quality.
Yeah, but I see, it's okay. The price is okay. The point is that if you pay, you at least can get it. Earlier, yes. Earlier it was like that. They will not allow you to pay, and they will not allow you to use, and they will keep on telling you, oh, it's not working, it's not working. And as I can just go there and see people working there and getting results out of it, but not working. The entire company was like that. So TM was not used for initially, but was working fine, something like that, and then it go. And if I would have been in charge, then what happened, then I would have been out of that. Yeah, definitely. Because I'm not for.
Do you guys know someone called Shubhashish Mojumdar? Bashu Mojumdar. So yeah, he was my PhD student's advisor when he did his MTech at IIT. Yeah, he does here at Kharagpur. Not me, my student who worked with me did his MTech here with Shubhashish Basu Mojumdar. Maybe I'll meet with him next week. He works on batteries. Head of what? Material science. Okay. Do we get started? It's been 10 minutes, I think. Yeah, otherwise we'll continue going for. Yeah. Okay, let's continue our discussion on using LAMPS software. I just showed you an example of just energy minimizing a lattice structure for aluminum, which is not really a molecular dynamic simulation. So now let's look at something more dynamic that involves equilibration and production run. The example I'll show you is basically simulating uniaxial strain on aluminum and calculating the Young's modulus. Okay, so we start now with the equilibrated structure that we generated, and I will share an input file that will help us run this uniaxial tensile loading of the single crystal. This doesn't have any defects, this particular compute input script. So the first part is pretty much similar to what we did in the previous input file. Now we are using a lattice parameter of 4.05 because we know that's what it should be. We are developing the crystal structure, so this is kind of a repeat of what we have done. So this is a bigger system. We are defining a block of 0 to 10, 0 to 10 and 0 to 10 angstrom. We will see how many atoms it generates. We are using still using the same potential model. A key parameter that we want to later visualize is called centrosymmetry parameter. I have the equation written here. It's a parameter that LAMMPS uses to kind of isolate atoms that are departing from its crystal lattice structure. Basically, at the start of a dislocation, you keep track of the neighboring distance of other atoms in the lattice through this centrosymmetry parameter, and it turns out that it's calculated in a way, thank you, that for a bulk lattice it should be 0, but as soon as you detect a non-zero number for this parameter, you can identify the formation of a dislocation or stacking faults, or if you have an atom in the free surface. So, these are parameterized, and you can use this essentially to visualize this system with the Ovito software to kind of check where exactly the dislocation is forming. So, we make the input file, calculate the centrosymmetry parameter for each atom in the system as a marker. I mean, what's the neighborhood of this atom? Is it in a bulk crystalline structure, or is there a departure from that as the system kind of evolves? So, the first step in the actual calculation is an equilibration run. So, in MD simulation, when you are trying to equilibrate, you have to set up the conditions. So, you are starting with time 0 and you need a time step now. So, in the previous calculation energy minimization, there was no time step because it was a static calculation. Here you have a time step of 0.001. So, what is 0.001? That is where the units come into play, are very important. In this case, the units are metal. So, the dimension for time, the units for time is picosecond. So, 0.001 is basically 1 femtosecond. But if you are using another system of units such as real, then I believe the unit of time, the dimension is for time is femtosecond. So, you just specify 1. So, you have to be very careful when you are writing up a file, because if this is incorrect, your whole simulation will blow up, because either you're probably using a very large time step, which you shouldn't. The next step is to create an ensemble of velocity for each of the atoms of the aluminum, right. We discussed this when we are talking about MD simulations in general. Remember the Maxwell's velocity distribution, speed distribution, right. We discussed this in quite details, and this is the velocity distribution that we can generate through this command in the input file, velocity in LAMMPS. It asks us to, we are asking it to create a velocity distribution for all atoms in a system. In LAMMPS, by the way, you can come up with definitions of groups of atoms. Let us say you are interested in modeling a system where you want to hold a set of atoms at the boundary static, then you can come up with a definition of a group of atoms, and then you would exclude that group of atoms in generating this velocity distribution. So, those are some things you can do. But in this case, we are creating a velocity distribution, and when we do that, we have to specify a temperature that it corresponds to, again through the Maxwell-Boltzmann speed distribution. It's related, the RMS velocity is related to the temperature of the system, right. So, we specify the temperature in this case as 300 Kelvin. The temperature units are pretty much Kelvin in most of these unit systems, metal, real, pretty much all except the Lennard-Jones. So, this is 300 Kelvin, and you have to use a random number, like kind of it's called a seed, to, because you are developing this velocity distribution in a random manner. It's not like you are specifying in a preconceived manner that atom 1 will have a certain velocity. You're just going from atom to atom and making sure you're capturing the right distribution that has the RMS velocity corresponding to 300 Kelvin. Okay. Now that you have generated a velocity distribution and the system is essentially at 300 Kelvin, the next step is, what is the boundary condition of the system thermodynamically speaking, and this is the definition of ensemble that we have discussed quite a bit over this past week. Like I mentioned, there are many very popular ensembles. The microcanonical ensemble, where you keep the number of atoms, the energy and volume fixed. there is canonical ensemble. In this case, we use what is known as the isobaric isothermal ensemble. So, what is fixed here is N, P and T, where N is the number of atoms in the system, P is pressure and T is temperature. Somehow I can't zoom in further from what's in here. Anyway, so that's what I'm telling the system. What should be the start temperature and the final temperature for this simulation? Both are set at 300. If you are trying to model thermal conductivity or some sort of a let's say the example I gave you for glasses, we were running a melt quench routine to get the amorphous structure at the beginning. If that's what I was doing, then I will start with an initial temperature of 300, maybe ramp it up to a certain high temperature and quench it. So, I can do those calculations. In this case, it's pretty straightforward. We are looking at a fixed temperature of 300 Kelvin. And there is a, if you are kind of changing the temperature, there is a parameter to say how quickly you want to do, basically the quenching rate. You can, that's not important in our case. Similarly, the pressure. So, we are holding it isotropically at 0 pressure. We are not subjecting to a system, this system to a certain pressure in any direction. So, this is a pretty straightforward NPT ensemble that we have described here. Once again, we want at the end of this calculation to output various parameters, energy parameters of this system. In this case, we choose to write at each write at every 1000 step of the calculation, which is every picosecond, 1000 times 1 femtosecond, right. We want to write the dimensions of the box, the pressure, potential energy and temperature, etc. If you look up the LAMMPS manual, we are certainly not limited to these. There are tons of other parameters that you can write out in your calculations. These are the ones that are most useful in determining, for example, if the system has equilibrated. So, the potential energy has to kind of minimize or reach a stable value, but you are not limited to this. You can even come up with your custom function. At this step, we are specifying that we want to run this system. How many time steps do we want to run? So, we define a variable n iter, basically the number of iterations somewhere here. So, at the beginning we defined a variable n iter and set it to be 20,000. So, we want to equilibrate this 20,000 time steps, which is 20 picosecond. This is typically just a guess. If you are far away from equilibrium at the initial or from the initial structure, then sometimes you might need to run an equilibration of several nanoseconds, but in this case we are starting from an aluminum structure that is already equilibrated. So, I think even 20,000 is not required, but we are just running it for 20,000 steps. Okay. So, that's all there is as far as the equilibration is concerned. Now, we are setting a couple of variables that we want to print out at the end of the equilibration. One of them is the initial length, which is the length of this box in the x direction, because we already know that in the production run we are going to impose a strain, a certain strain rate to the box in the x direction. So, we have a starting point for the dimension of the box in x. The next step, so this was the equilibration. The next step is actual deformation, the production run we are interested in. So, we reset the time step to 0, which is something you do not have to do, but it is very convenient to set it back to 0 for the production run. We again have to define some sort of an ensemble. So, in general, equilibration and production runs can be run with different ensembles. A lot of times, if you want to calculate properties based on Green-Kubo, which is an equilibrium based method, you do not want to disturb the system with a thermostat, because at the end of the thermostat, end of the day, the thermostat is kind of an added term to the Hamiltonian. Your energy is not conserved. So, the Hamiltonian is not the energy anymore. You have to add the thermostat, which is an expression in that function. And when you do that, that kind of disturbs the dynamics of the system a little bit if you have a pretty strong thermostat particularly, and therefore, your calculated properties will have a little bit of an error. So, depending on what you want to do, your equilibration, let us say, could be on an NPT ensemble, but the final production run could be a NVE ensemble. If you are doing an NVE ensemble, do you need a thermostat? Do you need a barostat? You don't need either, right? Because NVE means you're keeping the volume fixed, and the barostat is basically working on relaxing the volume of the system to get a fixed pressure. So, you don't need that. and you're running it with a fixed energy, where each box in the ensemble is not exchanging energy, and therefore its temperature will just relax by itself without you having to impose a certain value to it. So you might be thinking, and then see a question that what thermostat and barostat are in, are you specifying? The default thermostat in lamps is the Nose-Hoover, which is very, very popular. It captures the added term to the Hamiltonian in a pretty accurate manner, but you can choose other more recent thermostats. For example, the Bussy thermostat is very popular as well. It's a velocity scaling thermostat that is stochastic. As far as the barostat goes, the default one is called Parinello-Rahman barostat. Again, it's been around for a while. So, but you have options of using other thermostats and barostats for other applications. Okay, so you introduce a strain rate next, and in this case, the strain rate is pretty high because this is molecular dynamics simulations. You work with very high strain rates in general because you're dealing with pretty small simulation times. So, this is a very high strain rate that you introduce here. You're basically what you're doing is stretching the system along or straining it along the x direction, which we will capture in the movie. This simulation is probably going to take a couple of minutes to run. So, while I'm discussing this file, maybe I'll just start running it. That way it will be more efficient. So, you can see at the bottom it has this green bar and it tells you it's running. This is, it's even surprising that today we are able to run it on a tablet like this. In the 1990s, running this on even a desktop computer was absolutely impossible. But, today we can at least run these calculations. The first phase will be equilibration. It will go to 100%, then it will run the production run. Coming back, one cool thing as it's running that we can see is I really like this GUI. Like I said, something I'm exploring as well. It kind of plots the potential energy, whichever parameters that you kind of specified in your system. This is just the equilibration run. So, the change in the x direction is the third place of decimal or the second place of decimal, because you started with a pretty reasonable lattice parameter. So, it's not changing a whole lot, but in other systems you can see a pretty big change. For example, the temperature. The temperature actually is changing remarkably. It started with the initial velocity distribution, which was 300 Kelvin, but it somehow, as it was adjusting the box, it dropped to a kind of low temperature, and now during the equilibration phase it's picking up back to about 300 Kelvin, which is where it should land up at the end of the equilibration run. So, you're able to monitor all the variables that you're interested in, the potential energy, the length of the box, the temperature, as the simulation is running, and you can even see how many steps it's run. So, I set it up to run 20,000 steps. So, it's almost done, right, and I can come back to the code and it will show me the progress. Okay. In the meanwhile, let's continue discussing this calculation. So, what we are interested in outputting from this is obviously the strain and the stress, right. We want to calculate the Young's modulus. So, we define those variables for the stress and strain and write it to this file that will be generated at the end of the production run, which has already begun here. Okay. As the production run is going, I'm just curious, what is the potential energy? It's pretty flat, because you have an equilibrated system. It's not exactly flat because there is there is strain, but it's not fluctuating. It's not increasing a whole lot. So, we want to visualize this process. So, the lamps can kind of generate trajectories in many different formats, and each software that you want to use for analyzing these trajectories is picky. There are to what format it works with. For example, VMD prefers a certain format such as XYZ file. Atomi might prefer a CFG format. So, there are many different formats, which is how do these output files in the trajectory look like. Are we just writing the positions of the atoms? Are we also writing the velocities? Are we using angstrom units or nanometer units? It's in a particular order that we want to write? Do we want to include an atom type? So, all those things depends on which specific format you want to use. In this case, it's dumping in the XYZ format. This is a new feature in lamps. Again, something that I just noticed that it even makes a movie file out of this. So, you don't have to necessarily it's default. You can't, it's not customized, this movie that it generates, but you can generate a movie from this demo calculation here. You don't need VMD. So the movie is AVI file. In fact, I'm not sure my computer plays an AVI file, the latest Windows. So I should have probably changed it to a MPEG-AV or some other format, or GIF, GIF. That's pretty popular. So you can decide how you want to write that. It's basically an animation out of the. So we are almost done at 98%. So our simulation is run. So let's go back to the log file and check what we have. So this is a log file, okay? It's the comprehensive file that records both the equilibration run, which ran for 20,000 steps, and the production run. So it produces all the metric for, like in the previous simulation, the size of the system. This one had 4,000 atoms, so it's somewhat bigger, still pretty small. It produces the length of the box, which converges to 40.65 in the x, y, and z direction. And then it produces, so this one is more typical. You see the amount of time that the code spends on pair potential evaluation is about 91%. And that's the primary contributor here. And modify is basically calculating the thermal properties. And then this is the production run. So here it's calculating the temperature, which fluctuates because of the strain we are introducing to this system. At this point, let's try to visualize and see what the output file looks like as for the stress versus strain, which this code should have generated. Let's see. Okay.
The temperature effectively reflects adiabatic heating.
Right. Let's look at the folder was, I believe, tensile version 2. So it generated this file, okay, which has the stress strain, and kind of to make it easier, I already plotted it with Excel, the file that it generated. I just ran this one time before the lecture. Let's see. So this is the stress versus strain curve for the simulation we ran, and we can do a linear fit, and it spits out a number of 62.66 gigapascals as far as the Young's modulus is concerned, and I think it's close to what it should be. The literature reports it as at about 65 or 65 point something gigapascal. So the calculated Young's modulus is not too far off, considering we have a pretty small system that we are looking at. If I had to run this again, I would certainly scale up the system to much larger and probably play with the strain rate a little bit. So let's visualize what's going on here, okay?
So in X, Y, Z, those are dimensions?
Yeah, X, Y, Z are dimensions. In Y and Z, there is, we are not straining it in Y and Z direction, only in the X direction. So if we load it up with Oviedo, this is what we get, okay? And we can play a movie. If we play a movie, this one at the top, you can see that you're kind of straining it along the X direction as the simulation proceeds, but it's not telling us giving us a whole lot of meaningful information with this visualization scheme. So let's see if we can use the parameter centrosymmetry parameter that I introduced, which tells you where the atoms are departing from their FCC lattice structure, to get a better visualization of this. Let me try this out. Like I said, I'm just started using this software because VMD is not working on Windows. You have to do a color coding, okay, and color coding by the centrosymmetry variable, I believe. Particles. Give me a moment. Okay. Where is the centrosymmetry calculation? Give me a moment.
So you have to add it through the modification.
Yeah. I thought I did. So that's how I added the color.
No, so you have to add the centrosymmetry parameter also. It is towards the lower side of the list.
Centro. I didn't do it that way, I think.
No, you have to put it below the color coding.
Give me a moment.
List.
Let me
You
see.
have to put the color coding above. No, just go to the list. Click over color coding over there. No.
Just give me a moment. Hang on.
You can do that.
Let me load this up. Maybe I'm missing the right folder from which I loaded the Ovito software. Okay, so I think now it's working. So the centrosymmetry parameter is seen in the heat map. So as we get started, the blue corresponds parameter corresponds to a number that is close to 0, which is kind of capturing the FCC structure. But as the simulation proceeds to about, I believe, I'll slow it down a little bit. Maybe the frames per second is kind of, yeah, let's make it 2 frames per second, slow down the animation. So as we reach a certain stage of the simulation where the plastic deformation and the dislocation starts nucleating, you see the color code changes to a high number, which is basically telling us the location of that dislocation. But to visualize it even better, it might be useful to kind of remove the other atoms, and there is a way to do it. Let me see if I can come up with it to kind of remove. So here you can see the dislocation forming, but the surrounding atoms are still around. The blue atoms are still the FCC structure around the dislocation. And if you look at the trajectory, the stress strain characteristic here, I'm sorry. So this process starts at about 80% of the simulation has run. So about, there are total of 80 frames written. So about frame 60 to 64, that's where you start to see the plastic deformation, which is also captured from the stress strain characteristics. So let me see if there is a way to remove. Any questions?
Where is dislocation? Where is the dislocation?
So this centrosymmetry parameter kind of captures the departure from a certain crystalline neighborhood for this system. So it captures that. If the number is 0, it means you are in a bulk crystalline FCC phase for FCC crystals. If it is, a different number as it goes beyond 0, that just means that the crystal structure is, distorted.
Sir, for a very highly unsymmetric structure like a trifinic lattice, so in this, since it is considering the center of symmetry in picture, so in that case, sir, things change a little, or we have to.
The centrosymmetry, as far as I understand, is only defined for BCC and FCC crystal.
That is the cubic system.
Right, right.
the monoclinic type crystal structures, there are many compounds found as system. So in that case, the approach will be completely different.
I think so. You will have to come up with an alternate definition. Maybe the other way you can do it, besides getting into the centrosymmetry, is maybe visualize the per atom stress of the atoms in this system. So the centrosymmetry is a pretty convenient parameter, so to speak, to look at these simple structures.
Like we calculate for one thing and just
Right.
assuming it to be symmetric.
Right.
So in that temperature equilibrium step, why there was sudden jump at the initial?
When the system was initially equilibrating, why it dropped? That's a good question. We started with an initial velocity that was randomly distributed, right? And this is a periodic system. One reason that can happen is an atom at near the boundary is periodically interacting with its image, right? And the periodic image of the cell. So a lot of times what can happen is those two atoms can, due to that initially applied velocity, right? It's a Maxwell-Boltzmann velocity distribution. There's a peak. Maybe you applied a very high velocity to one of those atoms, and in its neighborhood that kind of got close because of the time step to its neighboring atom, which resulted in a very high velocity integrating the acceleration for the next step, and that would lead to either a drop or a spike in temperature depending on your system. One way, if you wanted to check this out, you can run this same calculation with number one, a different random seed, and this you might not see it happen. The second aspect is reduce the time step. Instead of keeping it at 1 femtosecond, if you reduce it to 0.5 femtosecond, maybe that will take care of it and you won't have either a temperature spike or a drop. But either way, it is corrected. In equilibration, all you care about is at the end of the run, you have a stable temperature, which was achieved. So I wouldn't be worried.
No, so with our input, is there any chance that the temperature overshooting, like does it drop so much to a low temperature that it cannot catch up to equilibrate in the further step, like maybe from 300 to let's say about absolute zero, or there is any chance?
That shouldn't happen because you have a thermostat that is, what it's doing is if it's detecting the RMS velocity of the system is going down, it depends on the relaxation time of the thermostat. What the thermostat does is it checks the temperature at regular intervals. Let's say you have specified a thermostat to check it every 10 picosecond. It calculates the RMS velocity and the temperature. If it is set to be 300 Kelvin and while your actual temperature is 285, then it will rescale the velocities to reach a temperature of 300, right? So this should work out. Now, what can happen is if you are checking infrequently every 10 picosecond, between 0 and 10 picosecond, the temperature can, especially for a system that you're equilibrating, it can shoot up or go down. But after a couple of iterations of correcting the velocity distribution and the temperature, it should stabilize. If it does not, usually what it means is the system is blowing up. What we mean by that is the force field is leading to somehow unrealistically high energy gradients, which shouldn't be the case. Let's say you have a force field parameter that went off and you use the incorrect unit. Instead of angstrom, you use nanometers or something like that. So that error will lead to a very high energy gradient, and that would lead to very high forces. In turn, you keep integrating it, your velocities will go up, and you'll kind of notice the temperature peaking even though you have a thermostat. That would basically mean that something is terribly wrong with your setup. Now, you might be tempted to say, well, let me use a thermostat to check the temperature every step or every 5 steps. There's a problem with that. You're shocking the system if you're continuously kind of scaling its velocity through that perturbation. So you want to have a system which has a very weak thermostat, by which we mean the relaxation time of the thermostat is at least every 1,000 steps, if not every 10,000 steps. If you're doing this very frequently, that's not really good for the the configuration itself as it relaxes. So it's a balance. During equilibration, a lot of times you have a strong thermostat every 100 time steps, while as you get to production run, you kind of make it weaker.
to how much extent we are controlling and this checking this temperature and all these things?
I didn't get your question.
Like you said about the frequency at which intervals we are measuring the temperature and all those things.
Right.
So depending on that, the measurement and the results are dependent on that?
It should not be. So there are recommendations from LAMS, like LAMS recommends, let's say for equilibration, thermostat, the relaxation time should be every 1,000 steps. For production run, 10,000 steps. So that's what you start with. Now you have a tricky system, very structurally messy system, which is not working. Then for equilibration, you start with a much stronger thermostat and a low time step, right? You equilibrate it for 10 picosecond, let's say. You go to the next phase and next phase. So you do it in steps in a way that your system equilibrates. Again, as long as your interaction potential is accurate, if it's just because of some bad contact or the way you set up the initial configuration, that should be corrected through energy minimization and equilibration, one way or the other.
So this is adiabatic process. This tensile testing, we are not supplying heat to the system.
So it depends on what ensemble you have set it up with. So if you have a microcanonical ensemble, that will be adiabatic. It's up to you how you want to define the ensemble.
This temperature is rising.
Right.
So can we keep system in such a way that temperature remains constant?
Again, temperature rising doesn't mean your thermostat is not working, because it depends on, if you have a very weak thermostat, like I said, you are monitoring the temperature, let's say every 10,000 steps, and you're writing your temperature every 10 steps. So there can be a situation where the temperature is increasing. It's because you haven't statted it, you haven't exchanged energy with another thermal bath to bring it down to what it should be.
What is cooling the system for the temperature? Affect the system. If we don't know what the temperature is, it affects the system.
Not to just know the temperature, it does not. You can calculate the temperature every step. It's computationally expensive. It would lead to very large dump files, but there is no problem. But if you want to adjust the temperature set the temperature, you use a thermostat to maintain a temperature, and you're doing that very frequently, then that impacts the dynamics of the system.
Yeah, as you are mentioning the weak thermostat quite frequently. So what does the strength of the thermostat exactly mean?
Strength, by using that word strong or weak, I'm saying how frequently you are using the thermostat. That's the only parameter you have let's say you chose a thermostat, nose Hoover. The only parameter you can play with is the relaxation time of that thermostat, how frequently you implement it. That's how I meant strong and weak.
So I hope that we will carry on with the a few more questions when we will be having lunch.
Talk to you about other aspects. This is by no means exhaustive. This is just a general introduction to the method, but happy to discuss your specific application that you're interested in.
So I would like to thank Professor Shomik Banerjee for presenting the last talk of this workshop session. Okay, and I please have a loud applause. So we will immediately come to our felicitation ceremony, and we won't be very long in doing this. We will make it as simple as possible. So the chief guest of this occasion is Professor Shibrat Singh, HOD of our department, Metallurgical and Materials Engineering. So thank you for coming, sir. So just I will give you a small overview I have written. So modern engineering applications like aerospace, automobiles, electronics, bioimplants, actuators, etc. requires effective structures and components, right? With improved safety precautions, right? Reduced, environmental impact,
These requirements include producing specific components using ultra-light structural materials, advanced high temperature and creep resistance material, nanostructure material. So, in order to address all these things together, we devised a small workshop like this on microstructure quantification and their mesoscale and atomistic modeling. So, in this workshop, we try to understand the quantitative microstructure and characterization of polycrystalline material, the microstructure evolution using the mesoscale physics and mathematical formulation, that is the phase field modeling, and then finally the atomistic modeling via molecular dynamics and density function theory to simulate, understand and predict the structure and property of various kinds of material, right? So, in this regard, first of all, I would like to thank Professor David P. Field for coming here in this tough little environment, tough little Mediterranean environment, okay? Then Professor Sinisa DJ Mesovrik, his mother got sick, so he had to leave. And finally, to Professor Shomik Banerjee. In this regard, finally, I would like to call Professor Shibra Singh to say a few words and felicitate.
Thank you, Professor Viswas, and good afternoon to everyone. I must first thank Professor David P. Field, Professor Sirisa Nesarovic, and Professor Shomik Banerjee for being here and putting up with this hot and humid weather of Kharagpur. Thankfully, it has been raining for last 1 or 2 days. So I hope it is better, but it was really bad for the initial few days. So I must thank you, and I cannot thank you enough for being here and devoting such a long time for our students. To the students, I will say you would have learned quite a few concepts. I would suggest that you start using it immediately. Otherwise, it is very easy to forget. If you leave it in your notebooks, then it stays there. You should start using it as far as possible in your own work, and that is how you will pick up. And I'm sure if there are some more doubts, they will be there over email, so you can always communicate with them, right? And then I will also thank other two faculty colleagues, Professor Sampa H and Professor Somjit Bishwas, for devoting such a huge amount of time for organizing this for your benefit or for our benefit, and then arranging it so nicely. Everything was done so well. So I must thank them. Let us give them a big hand to all these two people. And I would suggest that if you can take their feedback from the three faculty colleagues, if they have something to say about the way it was arranged, so that will be good. Yeah, yes. If you don't mind doing that. So we can then write it in our report that this is what we will then write it in the report that we have. So because he said a few words, I think I should end here. So thank you all. Thank you once again, and thank you especially you too, and to Professor Mesarovic as well. Thank you.
So I would request Professor Shibra Singh to give flowers to Professor Field and Professor Shomik Banerjee.
Thank you so much for your kind hospitality. Thank you. I hope everything went well. Very nice, very nice. We'll convey my regards to yeah, and I will expect him and you to be here during December symposium.
I hope so.
Yeah.
We'll come, yes.
So please have a seat. I would request Dave, can you say a few words?
Want me to come up?
Yeah, you can.
So I commend the students for hanging in there for kind of a long workshop, right? It's been a couple of weeks of workshop. And there's been 3 quite distinct topics that we've covered.
And I recognize that during the discussion, some of you are more interested in one topic than the other, which is good. So sometimes your eyes begin to glaze over on one topic that you maybe not know enough about to begin with, but these topics flow together very well, these three that we've talked about, and all of them will be relevant to your research in some way, all of these topics. And so I commend you for sticking in there, and the advice that Professor Singh gave is really, really good advice about starting to put this to use immediately, just starting to work on things. Even if you don't understand it completely, just get to work on it. So again, congratulations.
Thank you so much. Thank you so much. Thank you, everyone, particularly the organizers, Professor Aich and Professor Biswas. This was a great visit so far. I've really enjoyed doing the workshop and discussing some of these topics, which is atomistic simulations in my case. I'd like to thank the students for your attention. It was great to have the discussions, and you're an interested bunch of students, which is great to see. I would also like to thank the audiovisual folks. They did a great job in kind of making sure the presentation went as seamlessly as possible. Thank you for the facilitation, Professor Singh. I enjoyed the experience, and I'm happy to connect with you over email or Zoom if you have any follow-up questions on any of the topics that were discussed. Let's stay in touch for sure. Thank you.
Thank you so much, Shomik. So I would like to call Professor Shompaj. Please come. And I would like you to say a few words and then give flowers to our chief guest.
Okay. So it was a great workshop, I believe, although it is for a short time. I mean, if it is longer, it would be much better to understand and to have these great persons here for more number of times. But so far what we achieved and we received from them, that is our very good thing. I mean, it is we are very happy with that. And the students have learned many things, I think, and we also learned quite a significant amount of things from their lectures and participation. So I hope, or rather we hope, that in future we will have this opportunity again in a greater extent. So thank you very much.
Hopefully you will also visit us in Pune.
Yes, sure.
I would like to
And a big thanks and claps goes to the Professor Great Sanjeev Biswas to organizing the
So finally,
okay, and as I did the last time, I would like to give it to him also.
we will take together. Thank you. So it's over, and so we can proceed to lunch in the TGS guest house. Okay. Finished.
Nice to meet you again, and I'll be around next week, so I hope to meet with many other faculty and have some good discussions. So.
Are you going around also?